Hi there. In this video, we'll continue our discussion of finding the derivative formulas for exponential and logarithmic functions. Previously, we've handled y equals e to the x, which drives all of this discussion. And we've also looked at the derivative of the natural log function, and we found the formula 1 over x. In this video, we'll look at derivative formulas for exponentials with a base other than e, and logarithmic functions with bases other than e. Okay, a little bit of background before we get started. The approach that I'm going to show here relies on knowing the laws of logarithms. So let's just take a brief moment to review one particular property about logarithms. Okay, so the logarithm is really about finding the exponent that gets you to a particular number. So if I want to get to 25 cubed, which is 25 times 25 times 25, when I ask what's the log base 5 of that, I'm really asking how many 5s it takes to make that. So let's count. Here's the first 25, here's the second one, and here's the third. Okay, so we've got 2, 4, 6 5s altogether. So this value is 6. Okay, notice though that we can also relate this answer to just the logarithm of 25. So the logarithm of 25 is just 2. It took 2 of these to make 25. And so if you want the log of 25 cubed, clearly it's just 3 groups of 2. Okay, so 3 times 2 is certainly equal to 6. All right, and this just illustrates the fundamental law of logarithms, which is summarized here. Okay, so the rule is if you want the logarithm of a power, you can bring that power down and make it a multiple of the fundamental log. Okay, so that log rule is going to get used multiple times throughout this video, so I just wanted to review that with you quickly. All right, with that out of the way, let's find a formula for dy dx for the function y equals 5 to the x. And we'll begin by taking a logarithm of both sides. So we'll take the log of the left side and the log of the right side, and then we'll use the properties of logarithms to our advantage to find the derivative. Okay, here goes. So we have log y equals, and here's where I'm going to use that rule where we bring the power down and make it a multiplier. Okay, and what I'm going to do, just for the sake of being concrete, is I'm going to write an approximation for the logarithm of 5. So let's pop over to Desmos and see if we can just compute that over here. I'm going to go down here and type logarithm of 5. Okay, and as you can see, that's about 1.61 approximately. So I'm just simply going to write 1.61, knowing that that's just an approximation, but that should make it a little bit more concrete in terms of what's going to happen next. Okay, so let me just keep track of what I'm doing over here. The first thing we did was take a natural log of each expression, and then we just used a law of logarithms. Okay, and now let's go ahead and hit both sides with a derivative. We're going to take d dx of both sides. All right, now we've already seen that the derivative of the natural log function is just 1 divided by the input. Here the input is y, and y has its own rate of change, so the chain rule tells us to multiply them together. Okay, and on the right side, we want the rate of change of 1.61 times x, which is just 1.61. Okay, let me shrink that down so I can finish my work on one screen for you. All right, and as we proceed, we just want to solve for this quantity. So we'll multiply both sides by y, and we get 1.61 times y. And that's the derivative formula for y equals 5 to the x. Okay, we can of course do one more step as usual, which is to write the formula in terms of x. So let me go back to this guy, which tells us that y is equal to 5 to the x. So I can just take out y and write 5 to the x in its place. All right, so in summary, we have the derivative of 5 to the x is equal to 1.61 times 5 to the x. And let's just go ahead and interpret this result graphically, and then we'll come back and tighten things up a little bit. Okay, so let me just pop over here to the graph of e to the x, if I can locate that one. All right, so here I've typed in the formula e to the x, and we see that when x is 0, the height of the graph is 1, and knowing that the derivative of e to the x is e to the x, the slope is also 1. Here the height is e squared, or sorry, e to the 1, which is e, and so the slope is e. Okay, all right, so that's what goes on with e to the x. Now let's type in the formula 5 to the x. 5 to the power of x. And we see another exponential curve that's just rising more quickly. E is about 2.7, so here we're doing 5 to the x, so that should rise faster and have a faster rate of change. And if you ask, well, exactly how much faster is it than e to the x, this formula has the answer. In particular, it's about 61% faster in terms of its rate of change than e to the x. Okay, so that's just an interpretation of what we're dealing with. Okay, so for example, if we look at what goes on when x is 1, right there, for e to the x, the rate of change would be e to the 1. Okay, here we would look at 5 to the 1, then we would take 61% more than that, and that would tell us the rate of change. Okay, so now let me just go back and clean things up. 1.61 was used as an approximation for the logarithm of 5. So let me go ahead and just replace that with its true value. A little bit abstract here. And let's see, this would be the log of 5. I think I've erased my y symbol there. Okay. All right, so there's the technically correct version of the derivative rule. It's the logarithm of 5 times 5 to the x. Okay, so in the same way, if you wanted to do the derivative of 17 to the x, you can use the same technique, okay, as what was presented here. All right, so that tells us how to differentiate any exponential function with any base. And the result we got was the logarithm of 5 times the original function. Okay, so now we have that formula, and it remains to determine a formula for logarithm functions with a base other than e. So let's find the answer to that question next. All right, here goes. Once again, we're just going to rely on our knowledge of the logarithm properties and of inverse rules. Logarithms are inverses of exponentials, so let's use that to our advantage. We'll make a little bit more room for what's going to happen here. So I'll write inverse property is going to get used right now. So here we're saying feed x to the logarithm function and you produce output y. Let's reverse that. If you feed y to the exponential function, you should produce output x. Okay, those two statements are mathematically equivalent. Now let's use the law of logarithms. So I'll put law here. Or no, let's just take a log first, just to make it clear what's going to happen, not do two things at once. Let's just take the log of the left side and the log of the right side, and we get the following. Log 5 to the y equals log x. And now we can use the law of logarithms. So using the law right here, and so I can bring this power down and get a multiplier. Y times log 5 equals the log of x. Okay, and I'll again shrink this down so I can continue my work. And now we're going to hit both sides with a derivative. Okay, once again, this is just the number 1.61. It's just a constant, so we can use the constant rule here. We get the derivative of y times that constant. And on the right side, we get the derivative of log x, which we've seen before, has the simple formula 1 over x. Okay, and now we're just going to solve. So we would divide both sides by log 5, and that would get y prime isolated. So we get 1 over x, and when we divide both sides by log 5, we get the following. Okay, and that's our derivative formula for the log base 5 of x. All right, let's summarize. d dx of log base 5 of x is given by a rule which is similar to the natural log formula, but it has this adjustment to it. Okay. All right, so let's go ahead and look at that graphically and try to develop some sort of understanding of what this rule is telling us. Okay, so let me pop over to my logarithm function, if I have that up here. All right, so here's my natural log function. All right, and the rule here is that the slope is 1 over x. So when x is 1, the slope is 1. When x is 2, the slope is a half. When x is 5, the slope is a fifth. When x is 10, the slope is a tenth. That all looks right. So as you go further along the number line, the slopes are getting less and less steep. The rate of change is getting smaller and smaller. On the other hand, if you go close to the origin, for example, you put x as a half, you get the slope is 2. X is a tenth, the slope is 10. And so things are like really, really steep as you get closer to 0. Okay, so that's the natural logarithm function. If we look at another logarithm, like log base 5, okay, it has almost the same appearance. You might not even be able to tell the difference between the base 5 logarithm and the base e logarithm just by looking. Okay, but they are different. And the formula which we produced over here tells us that this constant number, okay, is just a multiplier that relates the slopes of the two functions. Okay. All right. So with that, let's go ahead and do a couple of application problems. All right. And what we'll do is we'll follow this same sequence of steps in terms of using inverse properties, hitting both sides with the log, using the logarithms, hitting both sides with the derivative, and then doing algebra to solve. Okay, now just to demonstrate that this is a reasonable approach, it just needs to be reasonably efficient. We don't always necessarily look for the fastest approach. We look for an approach that will allow us to use our conceptual understanding so that we know exactly what we're doing at every stage, but which is also reasonably efficient. So I'm going to go ahead and set a timer, and I'm going to compute a formula for dy dx using properties of logarithms and implicit differentiation. So here goes. All right, let me hit both sides with a log, and I'll just bring that power down as a multiplier. Okay, now I can take derivatives, 1 over y. Okay, and this is just a constant right there. So I just get that constant times the derivative of the expression in parentheses. Solve for y prime. And we can just multiply all this by y. Times y. And of course, y has this formula, so we can just delete that. Replace y with that expression, and we get the following. Okay, there you have it. In just over 1 minute and 10 seconds, I was able to compute the derivative of 3 to a strange power. All right, and along the way, I got to practice my skills with applying laws of logarithms and using implicit differentiation. Okay, so those are good things in and of themselves. All right, let's do one more application problem. Okay, What is the formula for dy dx if y is the base 2 log of x to the fourth plus 3x? And I'll again use a timer to keep track of how long this takes me. All right, here goes. I'm going to rewrite this as an exponential problem. Hit both sides with the log, bring the power down. Take derivatives. Use the constant rule. And let's see. This would be 1 over the expression times the derivative of the expression. And now it looks like I need to use division. So I just need to divide by log 2, and I believe that's it. Okay, and once again, right around the 110 marker, okay, to compute this derivative. And let me see if I can shrink that all in one screen so you can see my work a little better. Give me just a moment to adjust my screen here. Can I shrink that down reasonably? And now I'll just want to scoot this to where you can read it all. Okay, there we go. All right. So once again, in right around 1 minute and 10 seconds, we're able to compute these derivatives. And along the way, we're practicing our skills with relating logarithms and exponentials. Always good practice with that. We're using our skills with logarithms. We're using implicit differentiation as well as the chain rule. Now, one thing that I will point out is that I just applied the chain rule when I did this part of the problem. Okay, I'm treating this quantity as u, and then we get 1 over u, which is the fundamental rule for the derivative of a log function, 1 over u. And this right here would be the derivative of the u component. All right, so I hope that that's helpful to you, just in terms of understanding how to do problems, how to derive the rules. And let me just complete my table right here. So we did all the work. I believe we got the log of 5 times, let me see, I think I need to divide. We got 1 over x times the reciprocal of log 5. Okay, so this video is designed to help you understand how to use these results here to compute derivatives for any exponential or any logarithm function. Hope this is helping you to learn calculus, and we'll see you next time.